Exactly. Hey, you know what I'm saying?
Never want to wear a hat again.
You never want to wear a hat, right? Exactly. Okay, so let's drive this point home. I want to understand what this 1/6 means. And I like to always think of it this way. You're trying to explain what a 1/6 probability means to someone who doesn't understand statistics at all. But they understand like rolling a die. So if you had to explain rolling a die to someone, tell me what 1/6 means, and also tell me one thing 1/6 does not mean when it comes to the chance of rolling a die. So start with either one of those that you want. 1/6 means, what does the probability of 1/6 mean if you're rolling a die? What does it mean? You guys already have said it a couple times, but you've said it kind of scattered and in pieces.
Yes.
So be brave. Beth, I'm going to call on you, my friend, because this is the Beth Newman clause. I love it.
On average, over time, you'll roll a 6 1 out of 6 times.
Oh, I love it. I love it. I love it. So basically, what it means is, on average, over time, you'll roll the number 3 1/6 of the time. No, you said it. That was perfect, Beth. It was absolutely perfect. It was absolutely perfect. You'll roll 1/6 of the time 3s. You'll also roll 1/6 of the time 2s, or 6s, or 4s, or 1s or 5s. Exactly. Tell me something it doesn't mean. What doesn't 1/6 mean?
That every time that you roll 6 times, you'll definitely get a 3.
Aha! It does not mean that every single time you roll a die 6 times, you're not guaranteed a 3. Athena, what you said earlier was so cool. This is the problem with probability, the problem with randomness. I think you did the problem with randomness. And you said this is what makes it. You said it so. It was almost like you were almost frustrated with it, but you were accepting it as this is what happens. There is something behind the 1 in 6 or the 17%, but it's not a guarantee, right?
I was irritated because of gambling.
Well,
They tell you you have 1 in 6 chances,
but you do. See, that's it. You do. If you ever got, watch this. Crystal, go ahead.
You have a chance of getting rid.
You have a 1 in 6 chance.
which makes it sound
Every single time you roll. Friends, check this out, friends. Check this out. Check this. Let me switch this over. Let me see if I can see this.
Irritated.
No, it's not rigged at all. It's just that you didn't catch it when you wanted to. There's a difference there, friends. There's a difference. Somebody else got your 6 or you got your 3. Okay, so here, what I've done here is I've created, this is kind of what your third project is all about. When you'll open up Excel spreadsheets and use, they're called Monte Carlo simulations. So essentially what it does is it replicates an experiment like rolling a die using computer simulations. Now, what you just did with a real die is much, much better than what we're about to do here. Because what you hold in your hand is a true random number generator. There's a problem with computer random number generation. We saw it last week, didn't we? What's the problem with computer random number generation?
Computer doesn't kind of be random.
The computer can't be random, Athena. Perfect. So we got around this kind of last week when I made you guys do what with your TIs? Do you remember?
Set up your birthdays.
I had you all put your birthday in, stored it in the randomizer, so we all generated pseudo-random data. Same thing's happening here, although I've run this sheet so many thousands of times now. So here's what we're going to do. I'm going to roll this bad boy. There's 6 rolls. There's 6 rolls. That's what happened. That's what happened. Looks like I got 2 3s. I got a 2, a 1, a 6, and it looks like a 4. It looks like I missed 5 in there. I got no 5s that time around. So right here, we've disproved the belief that 1 in 6 means that if I roll it 6 times, I'm going to get a 3. In this case, I got 2 3s. I guess I didn't disprove it. I just got more than I was expecting to get by that definition. So what I'm going to do is I'm going to roll 6 more times. 6 more times. There. Now I rolled it 12 times. Look at that. It's the same proportions that it was before. Let's roll 6 more times. Okay?
5 still.
They've changed out. No 5s yet, right? Watch this. I'm going to hold down F9 and let it keep rolling. Did you see 5 just encroach in there now? Now what's happening, friends? Use my friend the stapler here if I can do this.
Oh.
What is happening, my friends?
It's
Equaling out.
Oh my goodness.
Overtime.
Oh my god. Oh my god. Actually, what's happening?
Over there.
There we go. That is pretty freaking cool, isn't it? Hang on. I need to get my, if I could just learn how to write macros on Excel, I wouldn't have to do this. Hang on.
Just staple it down.
Just
Staple it down, yes. IT would love me for that. Oh, is that working? No.
Staple it down.
Yeah, I mean, it's a good idea. This works so easily in the first class. Why is this not working?
Oh yeah. How about put a die on the key and
Yeah,
then
and then something over the top of it.
yeah.
Oh, that's a good idea.
8.
Oh, not quite enough. Hang on. I'll get home. Just stay here. So what? I'm going to use my hands. I'm telling you. What are you seeing? What are you seeing up there? Where is the 1/6 occurring? Where is the 1/6
6 different
occurring?
places.
And what about those places?
Well, they're different options. Like one.
Right, there's a 1, a 2, a 3, a 4, a 5, and a 6. And where's the 1/6 coming in? The fact that all 6 of those areas are what now?
Equal.
Equal. Equal-ish.
Yeah.
Now I want you to look at it a little more carefully. What did I stop at? Let me stop at an even multiple. Let's stop at 1800. Because that divides. Oh, crap. Well, that's close enough. Close enough. Let's pretend it was 1800, because it's arguably 1800 right now. If this thing were behaving purely perfectly, how many of each of the numbers should we have gotten after 1800 rolls? Go ahead.
300.
300 of each, correct? You should get 300 of each. There should be 300 ones, 300 twos. Now look at this. This column right here is keeping track of how many of each we got. 319 ones, 292, 295, 293, 303, and 300. Now, they're not 300 except for the very last one. And that one's not even completely correct because we rolled 1802, not 1800. But regardless, are they close?
Yeah.
Yes. You don't have to get perfect. You can get as close to perfect as you want. Look at this column right here, friends. That's the relative probability column, if you will, of what's going on. 18, 16, 16, 16, 17, 17% all the way down. Damn close to that 1/6 that you're seeing. So once again, we see that beautiful definition of what a probability of 1/6 actually means. It means not that you're going to get a 3 out of every 6 rolls. It means that you're going to get a 3 out of every 6 rolls on average and or over time. I'll say either one of those. Actually, honestly, I wish I could hold this down so we can let it keep going, but I can't. We're muted here. Honestly, the on average and over time is a little bit redundant. They both kind of mean the same thing. On average or over time. You can say them both by all means. They don't contradict each other by saying one and not the other, or both at the same time. But that's all it means. It's not a guarantee. Actually, leave that back up. It's not a guarantee of any of that. It's a guarantee of a long-run behavior. I made this, on the way up the hill this morning, I had an idea for a second sheet. Let's see if this is helpful to you guys to kind of see it. Check this out. It's called the law of large numbers. So let me see if I can make it so you can't see that at all right now. Here, let's shrink this down so you can actually see what's going on. There's a little bit more going on here. What I'm doing is I'm rolling 6 dice at a time on this one. And what I'm going to plot on this graph is every time I press F9, these dice pop over 1. There's a number of trials. So I attempt to go 500 trials. Which, now think about this. We just did the experiment of rolling dice about 220 times or something like that. This is able to do basically, and it's not just doing 500, it's doing 500 times 6. So you're getting quite a bit of result here. On the left-hand side is the probability of these rolling a 3 on each of these dice in the empirical way. Now, when I say empirical, I don't mean it knows that it's 1/6. It doesn't know that it's 1/6 at all up there. It doesn't know anything about the fact that it's rolling dice. What it's doing is it's randomly generating. So watch this. I'm going to press it one time. Okay? One time. Boom. Right there. Now, right now, that blue die up there came up 3. Which means 100% of the time that it's been rolled, it's been 3s. So right now, after one roll, it thinks the probability of 3 is 100%. Right. Because it only rolled 1, and that 1 was a 3. This green one right here, has 1 out of 2, which is 50%. The other ones didn't roll 3, so therefore they're at 0%. If I keep rolling, look what you start to notice. Now there are 6 different colored dice up there. What do you notice about the dice as I roll more and more? They're starting to stack. They're getting closer together. I like that. They're stacking. They're getting closer together. I'm going to make this a little bit easier to see. Hang on one
The chance
second.
of getting a 3 is becoming, no matter which dice you're rolling, is becoming
Closer to what, my friend? Keep going with
Each
that.
other.
0.16.
Each other, but
Each other and what?
the same average.
It's starting to zoom in on Michelle.
17%.
17%, isn't it? Check it out. I zoomed in the window, so now we're not looking up at 80% or 70% anymore, because once the law of large numbers kicks in, it's not going to go that high anymore, unless your die is somehow fixed, which we'll study that kind of stuff in Matthew 44. Notice, they spread out when I first zoomed the window in. But what's happening as I spin more and more? They're starting to cluster. They're a little bit low right now, aren't they?
Yeah.
They're a little bit low. There's 15% right there. Let's keep rolling. Oh, where are those guys headed?
Oh, we're moving up.
Oh, where are they headed now? Is that because the die have a memory? Is that because the dice are saying, oh my goodness, we haven't rolled enough threes, we better start rolling some more threes? No, it's the law of large numbers. Now, blue's getting a little out of hand right now.
Crazy.
But that's okay. I wish, it does work. Look at that. Look at that, friends. Look at that. And then, right at the end there, we're clustering right around 17%. The die don't know what they're doing. There's not even any die here. All that's happening is they're keeping track of cumulative totals. 481 trials. 481 trials. Divide that by 6, roughly 80, correct? Roughly 80. So you should be seeing 80 in each of these. Look at this. Look at how high these guys are down here. We got 98, 98. Those are actually very high. 64 is a little on the low side. It's funny. I gave this talk last weekend at Ormatic. I think I told you guys this. I had to give a couple presentations last week, and I opened up a similar file to this, and there was a lady in the audience that said, well, you know that Excel is a terrible randomizer. And I said, well, yeah, we know that. It's pseudo-random. She's like, no. It's going to roll the bigger numbers more than it's going to roll the lesser numbers. And I said, well, what do you mean? And she pointed to the sheet that I had open, not this one at the time, and she said, well, look, your sixes, there's more in your 6 column than in your 1 column. And I said, well, yeah. And then I pressed it again, and it still wasn't. I pressed it again, and it still wasn't. It's like, you see, I'm like, I've seen 3 trials. That doesn't prove anything. And this actually disproves her comment. If you look at all, now these appear to support her comment, right? Because it's greater down to lesser. But look at all of them. Look at this one up here. 64, 90, right? If that statement was true, I shouldn't see that. 71, 80, 75, 79, 98, 77. So in half of these, the number on the bottom is bigger than the number on the top, and the other half it's the opposite, which is, in my opinion, textbook case of not proving anything.
Where did she get that information?
I don't know. It was one of those things where I read it online. And I know Excel is not a great statistical tool. I know that. But I know that it's biased against randomness, but I've never heard that claim about its bias before. So, whatever. And I read a few more trials, and then it fell apart. It's like, oh, okay. And that's the beauty of scientific discovery. You have a theory, you create data. If the data supports it, you test it further. If the data throws it out, then you throw it out and you start again. So I was able to throw that out right there. Make sense? You guys see what's going on? So I think we now understand concretely what it means to have a probability of 1/6. Now, what we're going to start talking about now, this was not the project, is the idea of how to discuss the probabilities from an experiment in a concise way. We'll go over here. All right, so what I want to do now is I want to talk about organizing probabilities for an entire experiment. Not just the chance of rolling a 3, but the chance of rolling all possible values for the experiment. And this is what we're going to talk about, a probability distribution. Now you know what a distribution is already. You know what this is already. Because we've been looking at these for the past 5 weeks. A t-table, an x column and an f column. We've been looking at this, we've been averaging them, we've been standard deviationing them. That's even a word, I don't think it is. It is now. But what I want to do is I want to turn a frequency distribution into a probability distribution and hopefully motivate why the hell we want to do this. Hopefully I'll motivate why we want to do this in the meantime. So what we're going to do first, we're going to create a column, the x column, like we always have on the left-hand side. And the x column is our data, and the data is what we're interested in. And in this case, again, referring back to our original experiment, x is going to be the number of pips on the die if you roll a single die 1 time. A single die 1 time. Fair enough? And what values? Oh, pips is just the dots. It's a silly little term for the dots on the die. So, knowing that, what values of x can there be, can exist?
1 through 6.
Exactly. 1 through 6 inclusive. 1, 2, 3, 4, 5, 6. Beautiful. Now, what we've looked at in the past, and we actually looked at today, right off, we had a frequency column right here. And we actually had 2 frequency columns today. We had the experimental frequency column, and then we had the theoretical frequency column, the average frequency column, if you will. What I want to do is, I want to take what might seem to be an unnecessary detour and call this new column the probability column. And rather than keeping track of frequencies in this column, we're going to keep track of something that are called relative frequencies or probabilities. In other words, I don't want this column in any way to talk about the number of times I roll, but I only wanted to talk about that relative percentage of the time I get these things. So, if I roll a die, what's the relative percentage that I get 1? What's the percentage? What's the probability that I get 1? 1 in 6, or 17%. I'm going to leave it as a fraction if it's okay with you guys. 1 in 6 is one of those strange ones. 1 in 6 is a strange one because, simply because it doesn't terminate. So if we try, well, more on that in a second. Give me 3 minutes. I'll explain why I'm going with a fraction on this. How about 2? What's the probability of an x value of 2? It's 1 in 6. They're all going to be that way, Athena, because if you remember the way you so clairvoyantly drew that graph for us, the only way that graph can be a perfect horizontal is if all the y values are the same. And it doesn't matter. It doesn't matter if all the y values are 1/6, or what were they, 42.83, I believe was the actual average value. They're both going to be horizontal lines. One's raw counts and one's percentage counts. Now, this, I want to draw some other colors over here. We used to call this column the F column. I'm going to put F in quotes up here. And you can still think of it as the F column. It occupies kind of the same space as that, but I do want to refer to these 2 columns with some new terminology. They act the same, it's just the terminology changes, and there's a very good reason. I would not do this to you just to change terminology. There's a very, very good reason why I'm changing the terminology on you. This column right here, I want to call that guy the random variable column. Random variable column. The random variable column. Now, I get the variable part. What the dead giveaway you're talking about a variable? What's the dead giveaway talking about a variable? What letter do you see up there? You call it an X. Good. And Lucas just proved the point by throwing that die across his desk. Why is it a random variable? Why is it a random variable, friends?
Because
Say it.
Because it's random. I don't know.
Because when you throw that die, do you know what you're going to get?
No.
Do you know what you could get? Yes. You don't know what you're going to get, but you do know what you could get. And what you could get is listed in this list right here. And that's the beauty of that column. It lists all, I'm going to drop an old word on you from your first project, disjoint outcomes of your experiment. It lists all the disjoint outcomes of your experiment. When I say disjoint simply means what? Remember what disjoint means? Sometimes it's called mutually exclusive. You might not remember this from your first project. It's okay if you don't. Does anybody remember it? Let me ask you a question. If you're interested in rolling a 3, is it possible to simultaneously roll a 2? No. Or a 1? Or a 4? No. Disjoint means if this happens, the rest can't. So basically what it means is we don't know what we're going to get when we throw the dice, but we do know we're going to get one of these 6 things and only one of these 6 things. That's what disjoint kind of means. Fair enough?
Yeah.
Fair enough. Good. So that's the beauty of that die roll timed so perfectly right there, Lucas.
Yeah.
It's because you drove home the point of this column. You don't know what you're going to get, but you don't know what you could get. And that's exactly what gets gamblers into trouble. They can see the entire craps table in front of them. Every outcome right there in front of you. The roulette wheel, every outcome right there in front of you. Even if you can't see the cards, you know the deck of cards of 52, 4 suits, 13 ranks, 2 different, you know the entire population of what comes next. You just don't know what element of the population you're going to be getting on each roll or spin or deal. And that's where the random part comes in. That's where the random part comes in. Cool. This column right here, the probability column, the P of X, or probability column, the beauty of this column is it allows you to analyze the entire experiment at once without actually having to do the experiment. In other words, you can analyze a gambling game before you ever place a bet and decide how much money you're going to lose on average. Notice I said that. How much money you're going to lose on average. Because you are going to lose money on average gambling. And we're going to talk more about that on Wednesday. You are going to lose money on average gambling. It's a mathematical fact. I saw a cartoon once. It said, "Welcome to beautiful sunny Las Vegas." And at the bottom, which is, the sign actually exists, I believe, as you drive down the strip. There's a big sign that says, "Welcome to Vegas." There's a subscript underneath that says, "Generously paid for by those who are bad at math." And I don't think it's being bad at math, it's the lack of understanding of how fast you can lose your money playing some of these games. We'll analyze one of them in particular on Wednesday, and you'll see how quickly other ones can lose your money too. Anyway, what this column does, it basically lists all corresponding probabilities of the x's. Now, I know this isn't the most interesting. I know this isn't the most interesting distribution because all the probabilities are the same. I know that. And I promise we'll get into way more interesting ones. I promise. But this is a great one to start with because it's very intuitive. We've been playing with dice since we were very, very small critters. So dice are inherently nice to us. But in general, these aren't going to be the same. These aren't going to be the same. But for right now, they are, and that's totally fine. One thing I do want you to note, and this is true for any probability distribution, if you sum up that column right there, what are you always going to get? 1 or 100. I love how I heard 1, I heard 100%, and they're both correct. You're always going to get 1, which stands for 100%. Why does that make sense? Why does that make sense? Why does it have to be 100? Why couldn't it be less than 100? Or more than 100? Chester, say that again. Yes, and if you roll something, Chester, what's it got to be? Either it's got to be one of those 6, right? It's got to be one of those 6. You can't take it away, and you can't double dip. You can't roll 2 at once. So 100% of the time, you're either going to roll a 1, or a 2, or a 3, or a 4, or a 5, or a 6. What does or mean? Probability. What does or mean? Or means to add. So 1 6 plus 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 1 6 equals 100%. You see, it's all coming together. All this comes together. Fair enough? Now, big picture. Big picture. Good. We're doing good on time. I can get you guys to get some more data here in a second. Here's where I want to really fuse statistics into probability. Everybody okay with this distribution? I want to leave it up here for a while. I have a question for you, though. And this is where the analyzing of gambling comes from. But also, I hate to talk about gambling all the time, although this course exists because of gambling. It also helps you decide on insurance policies. More on that on Wednesday as well. I want to swing over to the sideboard. And I have a statistical question for you. On average, same experiment, roll a die one time. Roll a die one time, okay? On average, what do we roll? On average, what do we roll? I heard 7. We can't roll 7, can we? Only a single die. Single die, my friend. That's okay. You think of 2 dice, and you're right. You're right on craps. You're absolutely correct. Craps is one of my favorite games to analyze mathematically because it has the best odds for the player. No, I should say that. Well, that's true. It has the best odds. They still suck on average, but they're the least sucky. Yeah, that makes sense.
That's how I
Good,
learned.
good. That's how you learn, because there's at least something out. Good, good. They're better, team better than roulette. It's almost like flipping a coin. Almost. Smidge under, smidge under. So everybody do this real quick. Everybody roll the die one time. All right, one die, one time. How many ones do we get? How many ones? We get a one. How many twos? How many threes? How many fours? How many fives? How many sixes? Look at that. On average, what do you think we got? On average. How do you want to define average? We have 3 different ways to define average, right? How do you want to define it? How do you want to define it? The average, i.e. balance, the median average, or the modal average? Right. The modal average is going to be tough, isn't it? Why? What's the modal average for rolling a single die over time? They're all the same, which means they're all the mode, which is kind of tricky. I almost get nervous trying to talk about the fact using the mode with this one because they're all the same frequency. So can we not to ignore the mode, but can we ignore